I taught for about 46, 47 years at Harvard. And about 10 years ago, I just had this crazy idea that I no longer was interested in teaching students, but I thought the real problem was teaching teachers. And this insight was when I noticed that most of my colleagues were critics, but not teachers. They could look at something and say they're not good or strong or weak or whatever. But they actually couldn't say something constructive to the student other than try this. And that was just very unsatisfactory. And this has actually become what I do. Tess and I, and sometimes with Mike Flaxman, sometimes with Steve Irvin, sometimes with Juan Carlos, we give workshops to teachers. And now that my book is out, we've been doing this about once every month or once every 2 months somewhere. And in the course of this, in the course of teaching teachers, in a 2 to 3 day period, full-time, I've had a variety of insights about things that work and things that don't work for the design of relatively large, highly political, and pretty complicated problems. And I knew that I was going to come out here and give a talk, and so I made a set of notes. And I'm going to try to cover every one of these points, but every one of them with an example or two. And my talk is going to be in 4 parts, and it's going to be fast. The first part is, why is little time and small data important? And what does that mean for collaboration and the languages by which we talk to each other? Because I think I'm an honorary professor at CASA at UCL, and everybody there as a postdoc is interested in big data. I'm interested in small data. And the idea that you have to make inferences from small data is central to geodesign. But how do you do it? The second part and the third part of my talk are 2 examples. One was a workshop that Eric Whitner and Shannon, Tess, I ran, basically, in Japan, which was all digital with highly trained people, really, really top rate. And many of you know Keiji Yano and Izura Soma, and just serious geographers, mainly scientists, except the process of synthesis of the design, which the GIS world does not support. And the second example, or the first one that I'm going to show, is a workshop that Tess and I ran last week at the Autonomous University of Mexico City for faculty, mainly designers, which had no computer use whatsoever. All right? And I want to contrast those because they were each variations on a central theme of using a framework to get a design done with 30 people coming to one design. That was the problem. And they were highly political problems, very complicated, and real problems. And the fourth piece is, what's the priority for research that moves geodesign out of sketching serially into systems designs that come together in a synthesis, which is a very, very different way of thinking and a very different way of designing, actually, with some overlaps and some fuzzy boundaries, but they're fundamentally different. And I want to show some examples. Can I get the video going, please? My talk today will have a series of themes which I'm going to try to integrate in a series of example case studies which deal with systems thinking, the role of diagrams in design, the role of collaboration, and the idea that geodesign, more frequently than not, is going to occur with little time and small data. There's a whole debate about a definition of geodesign. The shortest, most elegant is one that Tess Canfield edited from my editing of Stephen Irvin's editing of Michael Flaxman's from 4 years ago. Geodesign applies systems thinking to the creation of proposals for change and impact simulations in their geographic contexts, usually supported by digital technology. Geodesign is an invented word. It's a collaborative activity, and no one need lose his or her professional, scientific, or personal identity. I believe that very strongly. I think geodesign is best applied in this set of middle scales. I think at the smaller scales, the design professions do very well. At the smaller size, rather, not smaller scale. At the larger size, I think the scientists do very well. The politicians don't do very well. But I think that it's in these ranges, from the large integrated project to the river basin, or maybe the river basin or the county or the nation, where the real change that affects people and their environments is going to take place. And the tragedy is that the design professions begin here and go this way, but not very far. And the scientists begin here with truths that are worldwide and don't do very well as they get to the smaller scale. And so this scale, where the most important activity takes place, in my opinion, is the place where the academic environment and the professional environment does the worst. We do the least of teaching. The secondary problem is that we believe that a student has to learn everything, whether it's a design professional or a scientist. And the reality is that geodesign and making change, I don't even care if you call it geodesign, making change at these scales is essentially a social political process. And that includes proposing the design. And we're not teaching and supporting people who either are the coordinator of that process or even the team members, and certainly not the general public. We're still modeling our work with one person controlling the pencil. And I think that's crazy. Now, we've done experiments here in Redlands about using different design methods for different scales of problems. And at these smaller scales, what I've called anticipatory, participatory, and sequential methods work perfectly well. And at the largest of scales, rule-based, optimizing, and agent-based models are experimentally used and practically used, and they work quite well. In the middle, the likelihood is high that the constraining and combinatorial methods are the best ones, especially when there's little data and little time. In order to collaborate, Norbert Wiener basically had a theory about collaboration, which was derived from radar and airplane wars in the Second World War. And he said, in order to collaborate efficiency, you need two things. You need a framework for collaboration and a basis for communication. And the basis for communication has three components, two things, a framework for collaboration and a basis for communication. And the basis for communication has three components, three essential components. One is a shared knowledge of the subject, the second is shared assumptions, and the third and most important is a shared language. And the reason for that is because the people of the place send messages through the media to the professionals, to us, the design people, the IT people, the scientists, and we receive meanings from the impression of those media. And we, in turn, have to talk to each other on the same basis. And eventually, we have to send messages and their expression back to these people who receive it, and from the impression they gain their information. And they make the decisions. And if we're not talking a language that we all share, how can it possibly work? The framework I've spoken about many times. There's a book about it. The book is going to be in 4 languages shortly. That's not the focus of this talk. I'm using my framework. The language is very important, and I believe that the language essentially in our brains, if we're experienced, is diagrams. And this comes from other people. It's not my idea. And the diagrams represent either things that you think are good ideas and you want to use them again, or things that you think are bad ideas, or you'd never want to use them again. And the third is the rules by which you decide whether it's good or bad. And diagrams have content and structure. And the structure can be spatial, it can be temporal, or it can be both spatial and temporal. The sciences are full of diagrams. And typically, when you see a lecture in the sciences, what you retain is the structure and the content of a diagram. You remember these things, or you call on them. And the design professions have diagrams also. And if you're an experienced scientist or an experienced designer, you have a sense of the strategic moves that those diagrams in your brain allow you to make in a problem of geodesign, whether you're coming from the sciences or from the design professions or both. Diagrams are important. And if the diagrams are going to be the language, the question is raised, why don't we design with diagrams? Why do we sketch? Because typically these diagrams represent the systems which we're trying to integrate or alter for the better. Sometimes the same diagram appears in the sciences and in the design professions. For example, Kevin Lynch's image of the city and Richard Foreman and Michel Gaudron's landscape ecology model are identical in their diagram. They name things differently, but graphically it's the same thing. The reason these three things are important is if you don't have a shared knowledge of the subject, there's no way to identify what the data, process, and evaluations are. If you don't have a shared set of assumptions, there's no way to identify the priority of the requirements. And if you don't have a shared language, there's no way to know what to do in terms of improving those systems. It's fundamental. And what that means is that in the design of a study in geodesign, or any design process if you really want to know, including an automobile, these people have to work together to know that what's going on in those three terms. I can't hand off my geodesign problem to somebody without them knowing what I'm doing, what our assumptions are, and what our languages are. It's not serial design, it's parallel design. That's a really important point. It's not one person, then another, then another, then another. It's everybody simultaneously working with known requirements from each other and then putting it together. Now, there are lots of ways of designing. And as I said before, I think anticipatory, participatory, sequential work best here. I think rule-based optimizing and agent-based work here. And I think constraining, combinatorial, and mixed work here. And the ways that you actually do it differ. If you're an architect designing a house or a landscape architect designing a garden, you make a dot, and then you add more, and you add more, and you add more, and you add more, and you make a design. And if you want to make another one, you start again. And you can change it at any given time, but it's essentially a serial process. One, then the next, then the next, then the next. If you're dealing at the global scale, you probably have rule or mathematical models where you have a set of characteristics that explain a phenomenon, and you collect the data across those variables, and you might get a design out of the end. Of course, we've done this. We've experimented, made designs with rule-based and optimizing models. But what happens when you're basically doing a design with systems-based diagrams is you're making a whole set of diagrams and putting them together and seeing if they synthesize. Do they interact properly? Does one screw up another one? And the design can be started simultaneously by different specialist teams and put together, not one person controlling the pen. And that's really important. I'm going to show you two different examples, both of which have used this approach. The first one was done last week at the university, the Autonomous University of Mexico. Anibal Figueroa, who's the dean and an old friend and colleague, is here at this conference. And the second one was Soma City, which is the city nearest to the north of the Fukushima nuclear disaster. And Eric Whitner and Shannon and Tess and I ran that one. And the differences between them are important. Both of them dealt with systems thinking and design. Both of them were based on the idea that simultaneously different groups of people will put the design together from specialist perspectives on what should happen. A real collaboration, not at the beginning, but at the middle ground and at the end. The first one is totally non-digital. I don't believe that geodesign depends on technology other than brain power. And there was no computer use whatsoever. First of all, that university doesn't have substantial computer use for all students. It's a poor place. It's in a working class area of Mexico City. The university locks at 7 o'clock at night. All right? This is not Harvard, and it's not Redlands University. The second one was all digital, except for the very first design that was synthesized. The Mexico one was mainly faculty. The Japanese one was faculty and advanced students. The Mexico was mainly designers. The Japanese was mainly geographers and scientists. Both had a real site. This one was an adapted problem, adapted because we thought we knew what was going on, but we're not really sure. And the second one is a real site with a real problem. Now, the philosophy behind it was very different. In the first one, we simulated 6 interest groups merging into one design. And in this one, in Japanese, we had 6 alternative strategies or scenarios merging into one. Both of them took 24 hours over 3 days, where the actual work was done in 18 hours over 2 days, and the third day was purely for setting up a presentation in public. So why apply geodesign in a workshop format? There are several very good reasons. The first is when using geodesign when there's little time and small data. Nothing is better than concentrating people and locking them up until they solve the problem. You don't do it once a month on meetings. It doesn't work. Lock them up, the problem will get solved. Or never get solved. That's also possible. The second is when working through the framework in order to understand it. We had a meeting this afternoon, which was very, very important. And the question is, how do you introduce the idea of geodesign in a collaborative environment in a university structure which doesn't know what it is and doesn't necessarily want it? And the reason is they don't understand it. So maybe they should understand it by volunteering for 2 days of their lives, and then they can say, screw it, I'm not going to do it anymore. Or, I like this, it's important, let's build it into our curriculum. The third reason is when starting fast to identify the central issues, options, and choices. Why not run through the problem fast in order to figure out what the question is? It's like a doctoral thesis. You know at the end of the thesis what the question was. And sometimes it takes a design to know what the questions really are. And working through a workshop format it's only 2 days. What the hell? It's really simple. And finally, sometimes it takes a design to know what's really wanted. Sometimes they say, oh no, that's not really what we want in public, and maybe try it again. But this time try it slower. The first is UNAM Azcapotzalco. This is a university right here in a working class industrial part on the northeast of Mexico City, a city of 20 million people. It's an area that is moderately dangerous and perceived as such, without insulting anybody. The architecture school with which we were working has 2,500 students, very bright people. I'm going to show us a presentation that was prepared on Friday. Some of it is in Spanish because it wasn't translated in time. Some of it is in English. Don't worry about it. And I'm not going to show you the substance. I'm going to show you the focus on the method. So here's where we are. These are the professors that were in the thing. These are the undergraduate students and some graduate students. There are about 30 people. And the faculty were senior people. That's Mexico City's core. That's about a 30-minute drive to the Universidad Metropolitana de Azcapotzalco. You can see the big roofs are industry. This is an industrial zone. The air pollution there was terrible 10 years ago. It's not that bad now. The area of influence is an area that's interestingly gentrifying slowly because the metro has been extended into this area, and there's a whole new metro station right here near the university. There's a techno park which has 10,000 people, new buildings. There's a new botanical garden, and this is a place that could be changed very dramatically, except there's thousands of people living in this part of the place who don't want to move. They've been there in a very stable environment for 100 years. This is what it looks like. It's Mexico City. That's the Techno Park. That's a major east-west road that runs through a historical village. It's a disaster. There's old housing. There's a new shopping center. It's Mexico. It's a very nice place with very friendly people, but it's pretty very complicated. Why are we there? Well, because the university wants to study what its environment is going to be like in the next 20 years. That's why we're there. That's the problematic. How do we solve this set of issues? Now, I want you to focus a moment on this grid, because it's going to turn out to be important. It's going to turn out to be really important. Because what we're going to do is we're going to build a design out of projects recommended by systems teams, which are rank ordered and numbered. And at the end of our design, we're going to know which projects and policies are in that design. We're not looking at the product of the design as a drawing, but the product of the design is a set of actions that need to be taken if that design is to be implemented. Visualization is not the issue. So, how do we work? Well, Tess, Annabelle, and I, and one or two other people met the night before, and a workshop is not a democracy. It works because I'm going to stand up there and I'm going to say, this is how we're going to work. I showed them an example from another workshop, and said, we're going to use the same method under time constraints in a set of teams, and we're going to get it done on German time and not Mexican time. And the faculty was shocked. I know that after the fact. They came up to me afterwards and said, we were shocked at how hard you were. And I said, well, I was doing it to get this thing done. And they said, yes, we now understand that. So this is not a democracy. This is a LED process, LED process. And part of that is we went through exactly the flow of information from evaluations to synthesis to impact assessment to redesign to another one, and then 4 different ways of making a decision on what to recommend. And so by the time we started at 9 o'clock, by 11 o'clock, the students were already working, knowing where they were going to be 2 days hence, and leading into the what, where, when. All right, this is our data. Our data is Google Earth, a set of photographs, and a base map in about 10 land uses, and anything that they can dredge up off the internet. That's all. Now, that may be unreasonably small data, and we don't know. I don't know what they looked up on the internet, but I didn't give it to them. They had to figure that out themselves. But most of the time, we worked on those 3 things: photographs, an air photograph, and a base map, without apology. The next thing is the process models. A group of us decided that there were 10 systems that were crucial to this place. They're not rank ordered. They are housing, infrastructure, education, industry, commerce, recreation, safety, transport, landscape and environment, and image and history. And so we basically said every one of them has a color, and let's ask for people who know something about these to volunteer for the teams. So these teams were selected first by people who said, I know something about the housing area, I'll work on that team. And then we filled in with the rest of the people who were not expert. And generally we had somebody who knew something, and knowing something is important. And so they made a model of evaluation. And that's the models of evaluation. They have only 3 levels. By the way, that's not the case in the other workshop. But these only have 3 levels. Red means stop. This place is pretty good. Leave it alone or improve it. Green means do something here. We've got problems. And clear means I don't know. All right? So by noon on the first day, we had a model and a map of evaluation. And now comes the point that's really, really important. We then asked each of these 10 teams, and only 9 of them fit on the slide, each of the 10 teams to propose 10 ways of improving their system. So each team had a color, and they met, And they produced a set of diagrams, which in the meeting that I had this morning with Bill's team would be called a partial solution. But it basically says, do this here, or do it here, or do it here, or do it here. Or don't do it here. Or it could be a policy that applies everywhere. And they're color-coded, and they're rank-ordered. So that's the evaluation. It says, please consider putting industry here. And that's number 1, 2, 3, 4, 5, 6, 7, 8, and there could be 9, 10, or 11. And each one of them has a number, tiny little number, and a phrase of explanation in Spanish. And this is not different from things that I've done 35 years ago, as I'll show you. And then they're all laid out on a table. Nobody presents anything. It's all silent. And everybody goes to lunch. You lay it out. When you're done, you go to lunch. And you come back at 1 o'clock. And at 1 o'clock, we create the teams that are going to propose change. And we make 6 of them. The local people, the politically green people, the residential developers, the industry and office developers, the universities, of which there's more than one, and commerce and entertainment developers. And again, we call for volunteers, and again, we fill in, and we basically say, you're going to have to change this area with a certain amount of hectares of change. And it's only at that point that we consider what the evaluations and projects are. And the first thing we ask these teams to do is to build a decision model, to take the 10 factors, the 10 systems, and in a Delphi method, in a real Delphi method, where they're giving points, 100 points to each of them, to rank order the importance to their client group of those 10 factors. And as you see by the color codes, they're all different, except industry is a member of those 3 schemes. In university, expansion is the top priority for the education team, et cetera. In other words, these different client groups have different priorities. And given the priority, they're now well prepared to listen to how it's going to work. And what that, if you go, I'll go back. You notice most of these are in a zip distribution. And that means that the constraining method is the best method for them to design, where they take the first requirement and they solve that problem before they move to the second one, and solve that problem if it fits best with the first one. Then they go to the third one and see if it fits with the second and the first, and they continue on. And I demonstrate that in an example by pulling the plastic sheets together in a sandwich of about 15 of them, dropping them on the light table. And they have to make one plan of the infrastructure and transportation and one of the other land uses and show that they've got that development. And then there they go. What happens is they have about a half an hour to study the 100 or so projects and figure out for their client which set are the likely best solutions. And then each team has 15 minutes to grab these, because it's not digital. There's only one copy of each diagram. Each team has 15 minutes to grab what they want, put it on a light table, and photograph it, and then redraw it on a single sheet of plastic. And that takes about 2 hours. And that's the first version. That's 15 minutes of plastic. And now you begin to see, because each diagram has a unique position in a column for the system and in a row for the priority, has a unique black mark on the plastic. And so we know exactly which pieces of plastic are in that drawing. It's not versioning at all. It's knowing what's in it. And if you take a normal plan, nobody knows what's in it. But I know what's in it because I've got those black dots. And then they redraw it. Just simple redrawing. Photograph it, trace it, redraw it. And now we've got our first design. That's the first design. And we've got that at about 4 o'clock in the afternoon, 4:30 in the afternoon of the very first day. And then what we did is each of the teams that did one of these 10 evaluations evaluates each of the designs. And if it gets 2 green magnets, it's really good. And if it gets 1, it's good. If it gets 1 red magnet, it's bad. If it gets 2 red magnets, it's very bad. So these teams are evaluating these designs. And this team has a problem. And this team is actually doing extremely well. And that's the impact assessment of team number 1. And they can talk about it intelligently. Why is it that you got 2 red magnets? Well, because you put your factory in the only park in the neighborhood. That's why. Idiot. Okay? But that's it. And now you do a second iteration to try to get rid of your red magnets and trying to keep your green magnets. And so everybody feeds back and redesigns. And they actually go through the exact same process. But now it begins to get focused when they start to know why they got those red magnets. And so this is the second version. And they had the second version by noon on the second day. It's 12 hours to get to the second version of their design. And we did the same process again. Marking in red, in magic colors, that had a 2 before, 2 red magnets, and now it's got 2 green magnets, so they got a lot better. And some designs got worse. For example, that design had 1 green magnet before, and now it has 2 red magnets. It was counterproductive what they did. It happens. So we've got 6 designs at 4 o'clock in the afternoon of the second day that have gone through 2 complete iterations. And the question now is, what do you do? 6 designs don't go. You can't build 6 designs. And this now becomes a judgment. But there are 4 ways that I find very comfortable in deciding this process. And I'll go through each of them. This is where we are. We have 6 teams with 6 decision models, with a first design, which is this one, the original selection of policies and projects. They're marked. The first version, which is just redrawn from this one, and this one, which is the second version and substantially changed. Substantially changed. We could have had a third or a fourth, but there's no real reason to do that at this scale. Well, the first one is competition scoring. It's as though you had a competition. And it's basically this. The winner is the one with the most green marks and the least red marks, and it's number A, the local people's design. It got 17. Second place was 12. So 12 can say to Team E, can say, is there anything we've done that would help this design? And you might compromise, add some things. But basically, this is how a competition is typically run. It's not the best method by any means. In fact, it's usually a poor method to decide finally. The second one, I'm sorry, and this is the winner. That's Team A, and this is Team A's design. And if this aligned a little bit better with the plastics, we'd know what we'd had to do to implement that design. All right. The second technique is something that you can do on plastic, but it's actually very hard to do by computer. And that is you simply take the 6 designs and you put them on top of each other. And you learn a lot. What you learn is if the color is bright, given the color code that we used, that means everybody generally agrees. And if the color is muddy, it means there's real fundamental disagreement. And this is the piece of land where there's a huge trucking company which really destroys this neighborhood with pollution and danger of traffic. Trucks, hundreds and hundreds of trucks go in and out of there. This is the new subway station, and that's the university. And this is a very important piece of land. And there's disagreement. That's important because you could switch scale. The third one is we know how many times each project or policy has been used. Why? Because we can count the number of black dots. So let's see, you see, and these are those are the 10 systems, and these are the priorities. And that means that a lot of people used these, that one is the most. So let's see if we can make a design out of those projects that were used by half of the teams, on the theory that maybe there's a coalition that can be built. And so we went to the plastic, and it took 2 minutes, and we collected all the plastics that we used more than twice or 3 times, and we put them together, and that's the design. It looks a little bit like A. And the fourth method is really of the most interesting to me. We had each team evaluate each other team on whether they were potential partners in a coalition politically. And they did that on the basis of whether my design was like your design. And it's still 2 greens, which means partner. 1 is close, -1 is not close, and -2 is never. And when you analyze who gave 2s to whom, in other words, if I gave your team 2 greens and you gave me 2 greens, let's get together, come on. And we ended up deciding that there were 2 sets of partners, 1 here and 1 here. And so that was the end of the second day. And we had 1 more day to make a presentation at 3 o'clock or 4 o'clock, I don't even remember, in the afternoon. And that morning, everybody came in, and we got teams A, B, and E to put together a scheme, and teams C, D, and F to put together a scheme. And look how similar they are, except this piece of property. Okay? And then we looked at those, and we talked to those people, and we said, well, you know, you really ought to study this piece of land. And we had a couple of architects and a couple of older men, faculty members, who lived in the area for 40, 50 years. And so they met, and by 11 o'clock in the morning, these are the faculty. And by 11 o'clock in the morning, they decided that they could, in fact, compromise. And they created this design, which basically said, take this trucking out of here, connect the entrance, one of the entrances to the metro with a new street to the university, put techno park, high-tech research related to the university on this piece, and housing and a park and some commerce on this piece, and leave the housing for the old, existing people alone, but improve the heck out of it, and expand industry in this place. And this was the final design. So it went from a decision model to a first design, to a second design, to 2 alternatives for political coalition that decided that they could solve their problem by compromising on the biggest single piece of land that was open to development, and they created this design. So that's the existing condition. Those are the projects that have to be done to do these changes, and some of these now can be designed by going down in scale, and some, like a new subway station, have to go regional in scale to design them. And that's the future land use that's proposed for the university area. And that was at the end of 3 days with the provost's chief planner at the university top administration participating in the workshop. That's the first example. No computing whatsoever, but a lot of thought by a lot of people who know what they're doing in a tightly managed structure. The second example is really, in some ways, much more serious. The earthquake off the Pacific was a magnitude 9.0. Everybody knows this. It was the most powerful known earthquake to have hit Japan, and one of the 5 most powerful earthquakes in the world since modern record keeping began in 1900. It was so powerful that the island of Honshu, that's a country, the island of Honshu was moved 8 feet eastward. In Tohoku, the land dropped almost a meter. There were 9-meter high waves in the city that we're working on. And in some cases, there were 40-meter high waves in Miyako, Iwate, and Tohoku. About 18,000 people died, 1,000 of them in the place that we're working on. And it caused the meltdown at Fukushima for other reasons, because they lowered the plant when they shouldn't have. And hundreds of thousands of people were evacuated. That's the tsunami. That's what happened afterwards. That's me and Mikiko. What happened in this part of Japan is they had multi-meter high walls to protect against the tsunami. And you could climb those walls, and then you go down to a little beach, which they have on the edge outside of the wall. But there's a wall, a real wall, at the ocean side. And that's gone. It's disappeared. It's gone. And so are the people who died. And that was the center of a city. Tohoku University, where Yuzuru Osoda is professor, was asked by the mayor of Soma City to do a workshop to help him and his council decide what to do, because they had lost their population. The old people stayed and the old people came back, but the young people didn't come back. And Yuzuru, who was a student and professor and teacher at Ritsumeikan, where Mike Flaxman, Steve Irvin, I, Tess have taught over a 15-year period, actually. They know our workshop. It's in Japanese, and they've taught in it for at least a 15-year period. They organized 3 universities with the cooperation of Esri to do this workshop, and Shannon and Eric Whitner came to help, and were very, very important. Here's the problem. The problem is there's a city with an earthquake zone right in the middle of it. The red is where people died in the tsunami. The city is right next to Fukushima. And this was, when we were working, the current nuclear radiation, where red means do not touch, and the government claims that yellow and green are safe. Whether the people believe that or not is a question. This was our site in 2011. That's our site. This was our site this year past, in 2013, when we came to do this workshop. First of all, there was some residual wall. And there was some temporary stuff, but that's not going to stop very much. The sandbags, basically. For a small tsunami, it might work. Big one, it won't work. The electricity is back. That's not nuclear. The roads are rebuilt. And this is interesting. This was urban. And everything is gone, and soil has been brought back in, and it's now potentially agriculture. And if it was agriculture, the nuclear contaminated soil is gone. Nobody knows where. And other soil has been brought in. There is housing. There's a stockpiling of emergency housing in Japan. And they built a lot of housing very fast. And it's one family, one room, in a housing design that can eventually be expanded to older people housing or family housing. But there's a shortage of housing. The upper slopes landscape, which is a very important traditional landscape in Japan, is intact, because only the coastal zone was damaged by the tsunami. And this may be in has nuclear problems, but it still looks pretty good. And the biggest cultural temple complex is on a high hill, and that's, again, it has nuclear issues, but it doesn't have tsunami issues. But the problem is the city is empty. There's no traffic. There's no pedestrians. The old people are at home. The young people are gone. It's weird. It's a silent, silent city. So what are we going to do? How are we going to work? We're going to do a 3-day workshop. That's Eric Whitner, Shannon, me, Yuzuru, Keiji Yano, Tess is taking the photographs. And we're going to have almost the same schedule as in the Mexican one, except this time we're going to work with computers. There's the faculty: geography, 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 disaster science. These are engineers. Landscape architecture, the manager, the chief planner of Soma City. Agriculture, geography, disaster science, information science, civil engineering, information science engineering, and each of them brought some students along. So we met them first. Oh, and these are people who do know all of the Esri software that's available, if it's commercial. They have it all. They use it all. It's your customers, okay? So the first thing we did, starting at 9 o'clock in the morning, is we went through the flow of information. What are we going to do in the next 2 days? We had to decide what the 10 factors are, and we did. And we decided for whom we were working. We were working for the mayor of Soma, the city government, and the residents. And so we took this young man, who's the chief planner, who is a geographer, and we gave him 50 magnets. And we said, Of these 10 factors, tsunami, nuclear radiation, earthquake, evacuation, ecology, high-density housing, low-density housing, emergency housing, commerce and industry, put 50 magnets in these 10 columns in their relative importance. And what he came up with was this diagram. I just drew it from this number of magnets. That's the number of magnets. The two equally important things are protect us from nuclear radiated areas and keep the industry if you can. Keep the jobs. The second most are ecology and heritage, which is very, very important, and keep the commerce if you can, and everything else is less important. And so we decided, again, that constraining and combinatorial were the two methods we were going to use. And we were going to work at a level of GIS that is relatively simple. Why? Because we don't have much time. Don't give me the idea that we need to do a big piece of research. I don't have the time. I've got 2 days. I need an answer in an hour and a half. And we went through the entire flow of information. And by 11 o'clock in the morning, they were ready to start. By 10:30 in the morning, they were ready to start. What, where, and when. So we built a base map. This is our base map. We decided, let's not study the mountains because they are nuclear radiated and nobody's going to go there for 100 years. Focus where the problem is. There's your grid, same as before. There's your color code, same as before. Those are the 10 factors. Those are the rank orders because we're going to go through the same process. Actually, we did it here beforehand. So there's our students building a process model. And these are the process models. Ecology, risk of earthquake, risk of tsunami, risk of evacuation, which Eric helped on. Replacement housing, high-density housing, low-density commerce industry. And those are the resulting maps an hour and a half later, 1.5 hours later. By about 2 o'clock in the afternoon, these were the 10 maps. And in this case, they're in 5 colors. But once again, it's the same color code. Red means don't. Green means do. And they're all in the same color code, which means everybody can read everybody else's maps. And it's not a visualization democracy. It's my statement that it's got to be green, light green, white, yellow, light green, light red, dark green. And everybody has to use it, or otherwise you can't talk to each other. And I don't care what the color code is, but you sure as hell need a color code. And then each team had to do a series of up to 10 or so diagrams of what to do about their system and rank order them. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there they are, this time on a magnetized metal board, because we didn't have flat white tables. Those of you who are worried about the space for doing geodesign, get metal boards and white tables on wheels. That's all you need. And wire it up for computing. So that's 100 and some odd diagrams. And then we created 6 change teams. What happens if nothing else happens? The current restoration plan of the city. Get smaller. What happens if the city purposely designs to get smaller? Maintain and rejuvenate traditional lifestyles. Build a whole new center, a whole new city, because yours is in trouble. And finally, get new people in, new younger people, by giving them free housing sites, which in Japan is a big issue. So I again gave a demonstration of these 2 methods, because here we had 2 things equal, then 2 things equal. So you could use this method or you could use this method. Actually, this one, the combinatorial, is the best one. And we demonstrated it, and then everybody had half an hour with their team to decide what to do. Then they could grab them and test them. They would photograph them. But this time, this is the first set of photographs of plastics. These are on plastics, 15 pieces where we know exactly what they are. And those are the diagrammatic concepts, basically. This time what they did, however, is they scanned these. They took the plastic. They scanned it and rubber sheeted it to fit the base map and the other GIS layers. And they had a GIS base plan. And they had that by 3 o'clock in the afternoon of the first day. Really. Then they had it, and they could adjust it for size, for shape, for area, for whatever it is that you want to adjust. Because the first one is diagrammatic. It's really, truly diagrammatic. And then they spent their first time making this one, which is roughly spatially accurate. And again, we know what's in it, because we just transferred that information. So we have a design, and we know what's in it. And we evaluated it by their relatively complex models by simply using a system that Mike Flaxman designed 15 years ago in Ritsumeikan University, which they've been using, and it basically records the models as a set of rules that applies to a design. And so these are terrible graphics, but there they are. If it's black, it means these people are in trouble on that system. And we said, no, that's not good enough. Feedback. So we did the same process again. So there's the plastic, there's the first design, and there's the second design, and then we're going to do a second redesign. And then some teams changed scale, and that was interesting. Because we had this design, there's a new community for young people. That's their scenario, the commuters. We want new young people by giving them housing sites so they can commute to Sendai, which is up here about half an hour away. And getting free land for a house is a big deal in Japan. So there's changing of scale. And Eric set this up as a, I don't know what it is. It's like City Engine a primitive version of City Engine. And finally, we decided, let's stop and let's make a public presentation for their review and design. So what did we have? What did we have at the end of 2 days? We had 6 plans, knowing what's in them. We had each plan evaluated against each impact. We knew, given this decision model, which plans were doing the best in green and the worst in red. And we presented them. We made the students present them. And after they each made their short presentation, the group of 6 students got up to answer questions. And then 4 experts who are from the area gave their opinion on what to do, a totally different way of deciding what to do. And they couldn't agree. And I gave the last comment. And I said, you know, these things are not in competition. You could do this strategy for the first 5 years, then do this strategy for another 5 years, and in 10 years, maybe you'll do this strategy, but let's keep the option open for doing this strategy. And that's what they decided was a good idea, to take the 3 designs and not move them in space, but move them in time. I want to show you the animation of the final solution for this. Move forward. I may need some help, guys, because I had a problem before and people did help me solve the problem. And all right, there it is. There's the design. There's the new community next to the railroad station. This was a city. 1,000 people lived here, and 1,000 people died here, and it's now agricultural land. There's a new road on a dike, and we're going to build 2 barrier beaches and make a park out of barrier beaches. This is low density. This is high density single family housing, very high density single family housing. This is higher density apartments. This is the community core of schools, different schools and government. That's industry and commerce. That's a large park. That's a large parking lot for events that need hard surface. There's another commercial industrial zone here. That's the railroad station. That's the existing buildings that are left in the town. The area up here in the mountains is radiated. You don't want to go there. It's color-coded. I'm not interested in realistic animation. I'm interested in color-coding it for its land use, so people know what's where. The roads through the community lead you to, through agriculture, which is a new land use, to a park, which combines 2 artificial barrier beaches, one out here that's big and one out here that's smaller. And the 3 barriers that replace a wall that's 4 meters high is a barrier beach, and a road that's 1 meter high that you can just cross over with simple grading. And the community is built just outside where the first tsunami stopped and broke the wall and stopped. And that's the design that they've adopted as their long-term strategy. Now, it may not be built. Something may happen. And in fact, something did happen. About two or 3 months after we did this study, it was disclosed that there was groundwater pollution from Fukushima, and nobody knows where it is. So who knows what's going to happen? I want to make 5 more slides, if you'll allow me. The implications for education in geodesign. We really have to move people from the idea that there's one person that knows everything here and here, and get them to think collaboratively and politically, basically, as designers. These are political, important problems. Mexico's growth, and what do you do after a disaster? They're not fun. They're serious. The core is diagrams. We really need to deal with the management of diagrams as a design method. I've been doing this for a long time. This is 1967. That's me. All right? And in 1967, 68, Peter Rogers and I, Peter is an engineer, a hydraulics engineer, and I, that's me, built a system of models in the earliest versions of computer graphics. And it was iterative, and we grew Boston in 5 phases. We grew the southwest sector of Boston. And what we really did was we used a human agent-based model. So the idea that the systems determine what the future is at least a 50, 60-year-old idea, and we didn't invent it. Believe me, we didn't invent it. We used it. In 1980, in the Bermuda project, which is in my book, I had my students diagram to scale every idea that anybody had and rank order them. So these are now rank ordered by system and rank ordered by diagram. And this took a week, but these designs took 2 weeks. Why? Because I made each student pick a different set of diagrams to do a design. And they used a sequential method. And eventually they decided, the people of Bermuda, what to do. But the method of coming between these diagrams and these were do the diagrams, put the diagrams together, and it'll tell you the basic partie of the design. Don't start a drawing in the upper left-hand corner. In Tepoztlan, with the same people in Mexico, when we did this study, we had about 100 diagrams. Each were numbered. Each were on plastic, but then they were drawn digitally. We drew the diagrams. And this is Project 55. And Project 55, there it is again, is part of the environmental scenario. It's not in the tourism scenario, and it's not in the economic scenario, but it is in the compromise scenario. It's this green set of lines, keeping the green corridors in the drainage. And by the time we did that, it was 3 weeks into the semester, and in the 5th week we had a master plan for the area, and then we did 30 projects, some on the internet with the collaboration of Mexican students in that studio. It was very, very fast. The next year, Juan Carlos Vargas Moreno did something very clever when we were working on a project in Padova, on the largest industrial park in Padua. And he basically took 250 diagrams that were digital and linked them to an Excel spreadsheet. So a student could go and say, I want numbers 1, 15, 32, 33, 34, and 110, and 115 in this order, and the computer program would take them out of the Excel spreadsheet and drop them on top of each other. But graphically, the top one covered the one below, so it's not a good graphic system. Still a big problem, but we were able to automate it. This is the step that is essentially the creative step, and don't tell me for a minute that it's not creative. I don't think you can imagine the energy in a room when a group of people who are adults and professors have to solve the synthesis problem in 1 hour. You should hear what goes on in those rooms. It's intense. And the issue is the synthesis of ideas that have come, who knows where the idea, they're all anonymous, who knows where the idea came from, but they're ranked by the people who decided these are important ideas for our system. But what about this? What about the urban observatory? If these were the diagrams and all I knew, I need to do this, then this, then this, and I could point to them, wouldn't that be simple? And have a computer software put them together and rearrange them in rank order and tell me what I'm doing and just fill in the black boxes in the grid. I met with Bill's team this morning, and it's clear that that's possible. It just hasn't been done. And this is the central synthesis piece of geodesign. The rest of it is easy to do. Not easy to do, you have to know what you're doing. But this is the synthesis step. And if it's not synthesis, how the hell is it design? And finally, why not smart diagrams? Why not have a series of rule-based diagrams that say if you have unconnected open spaces, why not connect them? And you don't have to do anything. You just set a rule based on connect the open spaces, and pff, it connects. And I want to see that integrated. Because if I can have a set of diagrams and a set of intelligent people who know what they're doing, and I have it rigged up with rule-based and non-rule-based systems that can be selected and overlaying, added to with smart diagrams that can produce that and put it on top of that, that's all I want. The rest is city engine to make it look good and some intelligent people to define the problem in the first place. And that's what we don't have. And as long as geodesign applies systems thinking, why not systems design? And that's what we don't have. And in my experience in the last 5 years, teaching in that framework, I have no trouble at all convincing people that it's a good idea. And I don't have any trouble at all convincing faculty that it's a good idea and that they ought to consider designing in different ways and teaching in a different way. But it means that the software support has to support the way systems thinking and systems design operates, because the drawing is good. Bill's doing a great job on that piece. But nobody's doing that piece, and that piece is going to rule. Why is it going to rule? Because that's the scales at which it's best used. Thank you.